Dear viewers, Shoaib Dayo is here with a new lecture of the electrical machine subject, and today's topic of electrical machine subject is why transformer is rated in kVA. In our electrical machines, all the electrical machines are designed on the basis of the apparent power. There are the three types of the power. Number first is that the apparent power. Okay, so apparent power is that P is equal to VI. And second is that active power, so that it will be P equal to VI cosine of phi. And third is our reactive power. Okay, so it will be VI sine of phi. Okay, so all the electrical machines are designed on the basis of this apparent power, which is the product of the voltage and the current. Why, for example, in the case of the electrical machinery here, transformer is designed on the basis of the VA rating because the power factor is unknown. A manufacturer which will manufacture the transformer or designing the transformer, you do not know that which type of the load that can be connected with the transformer. So the power factor, it depends upon the nature of the load. Okay, so what is the power factor? Is that cosine phi angle between the voltage and the current is called the power factor, or it is the ratio of the resistance over impedance is called the power factor, or it is the ratio of the your active power over apparent power is called power factor. So here from the line we can see that the copper losses depend upon the current and iron losses depend upon the voltage. So here the copper loss is the variable loss. Why? Because the copper losses are totally depend upon the nature of the load, and it is because of the ohmic resistance in the winding. So if the copper losses are the variable losses, that considered to be the variable loss because the load is varying in nature. But what about the iron loss depend upon the voltage? When the transformer is energized from the supply, the amount of the voltage is fixed and the frequency is the same one. So your iron losses is the sum of the iron loss is the sum of the hysteresis loss, okay, and plus AD current loss. So both these losses, if we are combined, then they will show the iron loss. Hysteresis loss is the phenomena of the flux link still lagging behind to the cycle of the magnetization, that will be called as the hysteresis loss. The hysteresis loss can be minimized by using the low hysteresis curve material like silicon steel, which is used for the made up of the core of the electrical machine. And the recurrent losses can also be reduced by providing the thin laminations. The core is divided into the different thin lamination parts, so that eddy current loss or circulating currents can be also minimized. Okay, so what will be the total loss in the transformer? The total loss in the transformer is the sum of the variable loss plus constant loss. Here, what is the variable loss? Our copper loss is the variable loss because load is varying in nature. And what about the iron loss? It is also the fixed loss because here amount of the voltage that will be given to the transformer primary winding is the fixed one, and the transformer which is operate at the constant frequency either on the primary side and on the secondary side, the frequency is the same one. So your iron losses is depend upon the your voltage and also the frequency, so it is going to be called as the constant loss. So total loss in the transformer is depend upon the volt and ampere product, but not the phase angle between the voltage and current, because what is the power factor? The cosine phi angle between voltage and current is called power factor. So as you can see from the formula, cosine phi is the ratio of the active power, okay, divided by apparent power. Okay, so here what is active power? VI cosine of phi, and what is the apparent power? VI. So as you can see, the power factor has direct relationship with the active power and inverse relationship with that apparent power. So apparent power is that the product of the voltage and current, but here the power factor is unknown. Why? Because there are the different types of the loads that have the different power factor. For example, if we are talking about the resistive load, okay, there are the three types of the load in the power system: resistive, inductive, okay, and at the last the capacitive loads. Okay, the resistive loads that shows the unity power factor. Okay, inductive loads that has a lagging power factor, and capacitive loads has the leading power factor. So while designing electrical machines, we did not know what kind of the load that will be connected with the transformer. So here, while designing of any electrical machine, for example here in the transformer, why these transformers are rated in the kVA? Because the K shows that the value of that kilo, because our power transformer, our large transformer are rated in the terms like kVA, MVAs. Okay, so here the not only the phase angle that we are going to consider over here. Okay, so it is independent of the load, the power factor. So power factor is the ratio of the active power over apparent power. So power, you can cross multiply this apparent power multiplied with this power factor, so you can calculate the active power. So load power factor depends upon the nature of the load, and kW rating of the transformer will be different at the different load power factor. Means for example, the kW rating active power rating is different for the resistive load. kW rating different for active power is different for the inductive load, and active power is different for the capacitive loads. Okay, so the temperature means that's why the rating of the transformer is always given in the kVA, not in the kW. Okay, so temperature rise of the transformer is directly proportional to the apparent power kVA which flows through it. Means if the core is to be energized from the main supply, obviously the losses are being produced, okay, the iron losses, and if we are calculating the total loss in the transformer, so it will be the sum of the constant loss plus variable loss. So we can, just because of that increasing in the losses in the transformer, the temperature will rise in the core of the transformer, so that will be totally dependent upon the product of the voltage and current that will be called as the apparent power. So this was the explanation of that why the electrical machines are like here. The transformer is rated in the kVA, why is not rated in the kW? Because while designing an electrical machine, either in the transformer or alternators, so electrical machines are designed on the basis of the apparent power, because we are not considering the phase angle between the voltage and the current. So if we are considering the voltage and the current phase angle, so it depends upon the active power consumption, which is totally dependent upon the nature of the load, and that has the different load power factor upon the different conditions of the load which will be connected with any electrical machine. So this was the lecture regarding the transformer rated in the kVA. Now I'm going to summarize this, that how it is going to be the rated in the kVA rating, because we have considered the copper loss and also the iron loss in the transformer. The copper loss are the variable losses and the iron losses are the constant losses, because the frequency and the supply voltage which is given to the transformer is the same one, so that will be called as the iron loss will be considered as the fixed loss, and copper losses is totally depend upon the ohmic resistance of the winding and nature of the load, so that will be the variable loss. So total loss will be the sum of the iron loss plus the copper loss, and here we are not considering any phase angle between the voltage and current, so that's why the transformer are rated on the basis of the apparent power kVA, not in the kW. So this was the lecture regarding the transformer based on the kVA ratings, not in the kW ratings. So I hope that you have understood today's lecture, and at a loss, please subscribe my YouTube channel Shoaib for more informative videos related to this engineering area. Thank you.